I'm Amy Lambert, EA's Director of Communications, and welcome to this, our third in our series of webinars as part of our 50th anniversary celebration. Now I'd like to introduce today's speakers who will be providing their perspectives on the state of PFAS science. Paul Caprio is EA's subject matter expert for more than $90 million of PFAS-related projects. Masa Madiri is an environmental engineer and chemist who has served as a principal investigator for numerous PFAS research projects. Cynthia Cheatwood has recognized expertise in standard human health risk assessment practice and guidance. And Mike Hertz is EA's National Service Line Program Manager for Site Characterization and Remediation. Our first speaker today will be Paul Caprio.
Okay, hello everybody. I'm going to cut off the camera here to have better connectivity. Thunderstorms coming our way. So let me just turn that off. So good morning or good afternoon, wherever you are. So I think it's a safe bet that most people on this webinar had never heard of PFAS 10 years ago. I'll admit that I didn't pay much attention to it for what we referred to as PFCs or perfluorinated compounds back then. But we all know that PFAS are a group of synthetic fluorinated chemicals that they're used in a wide variety of industrial and commercial applications. You know, you can debate how many there are, but, you know, suffice to say that there are many thousands, but only about 600 or so are routinely used in commerce today. But if we fast forward today and look at how PFAS science has evolved in a relatively short period of about 7 or 8 years, much faster, say, for example, than it took for our industry to address other contaminants like TCE, which took, over 30 years. During this period, there's been, thousands of peer-reviewed scientific research papers that have been published. New analytical and treatment technologies have been developed. And to illustrate my point, just look at some of the agendas of some of the more prominent environmental industry conferences like Battelle or REMTech, that PFAS subject matter has dominated the agendas in recent memory. And, we're seeing the rebirth of the remedial investigation process after a relative downturn since the early 2000s. And now we have a better understanding how prevalent and persistent these PFAS are in the environment, as they've been detected in human blood serum worldwide, in drinking water supplies, atmospheric fallout, and they're responsible for nearly 150 fish consumption advisories in our nation's waterways. Next slide. So like everything else, PFAS have a life cycle. They are produced and used in a wide variety of manufacturing and commerce and used for occupational applications where there's a potential for direct exposure. An example of that would be firefighters who use aqueous film foam or AFFF for fire training purposes. Commercial products and other PFAS, like some waterproof clothing or stain-resistant carpet or cosmetics, can also eventually reach the consumer where there can be direct and prolonged exposure. And of course, these industrial wastes and these consumer products are eventually discarded into landfills and sewer systems where they end up in our soil, air, and water. But some of the more prominent sources of PFAS include the former AFFF releases at fire training areas, around PFAS manufacturing facilities, landfills, wastewater treatment plants that collect, a combination of municipal and industrial pre-treatment discharges, as well as sometimes they collect some of the combined sewer outfalls, all of which contain measurable levels of PFAS. So these chemicals are virtually everywhere. Next slide. So to illustrate the point about PFAS being everywhere, PFAS are present in wastewater treatment plant biosolids that are land applied for fertilizer in agricultural fields. They can accumulate in fish and other wildlife used as food source. And PFAS have also been found at measurable levels in precipitation over large parts of our country. So with this pervasive PFAS in the environment, whose problem is it? This figure shows 3 clusters of various types of commerce and exposure groupings. The x-axis on this figure represents increased accountability or liability of the specific group, and the y-axis represents increased benefit to that group from either use or processing or sale of these PFAS-containing materials. So the upper right corner group a cluster of groups. They represent the major raw chemical producers like 3M and DuPont, who've already been subjected to multi-billion-dollar litigation and settlements. The central grouping of clusters or cluster of groupings represents consumer products that either contain PFAS or use PFAS in their production or specialized use of PFAS containing products that have received some of the more high-profile public attention, such as fast food containers, cosmetics, Teflon, and have also included DOD for their use of AFFF in their fire training exercises. The lower left group are basically more or less the innocent bystanders, the occupational and consumer exposures, who are at the greatest environmental risk in landfills, wastewater treatment plants, and public water utilities, who have the greatest potential to be impacted by some of the proposed PFAS related regulations. So all these groups are stakeholders. The lower left group are seeking litigation options because of the possible health effects, environmental harm, or cost of drinking water treatment. Right now, the deep pockets are DOD and the major PFAS manufacturers, but at some point others will most surely be pulled in. Here are some examples of how public opinion in litigation has pushed up against or ahead of the science. Water utilities have banded together to enter into a multi-district litigation process against the major PFAS producers. 3M has settled a $10 billion agreement to support remediation of public water supplies impacted by PFAS. And you may have also heard about the firefighter suit against PFAS chemical producers due to health effects from occupational exposure to PFAS. This is an example of how the regulatory process has driven down PFAS guidance values in drinking water over the past 15 years, nearly by 5 orders of magnitude. There's no federal MCL yet. However, the proposed draft MCLs are up for 6 PFAS, including PFOA and PFOS. EPA indicates that these MCLs will be finalized by 2024. 28 states have also published guidance and criteria for drinking water and groundwater. EPA has developed a strategic roadmap that lists some major regulatory milestones. This guidance is also included some development and some recent memos that help regulatory agencies exercise their authority on administering NIPTIS discharge permits. These are a couple of regulatory milestones that may affect water utilities and drinking water and landfills and wastewater treatment plants over the next several years. EPA is also revising their guidelines for biosolid land applications, which will likely affect how we manage these materials when they're applied in protected watersheds, not to mention how they may affect wastewater treatment plants, certain industries, landfills, airports, and water utilities. Next slide. So before I turn over, is a couple observations that I'd like to mention. The analytical methods that MASA is going to discuss are now achieving lower quantification limits. We can analyze for more matrices, including air, a larger number of specific PFAS. So what that means is we'll find more PFAS where we look, but it's definitely caused a drain on the commercial laboratory. So environmental forensics, some of the 3D visualization, site characterization techniques that Mike's going to talk about. Cynthia's going to talk a little bit about why we can't settle on a safe drinking water level for PFAS. Why is this? And then I'm going to end up talking a little bit about some of the tried and true ways that we deal with PFAS contaminated groundwater and soil, and or any of the new technologies offering promise. So I'm going to turn it over to Masa at this point.
Thank you, Paul. So I will switch the gears a little bit here, and I will talk about the analytical methods. So as we all know, when it comes to managing contaminants like PFAS in the environment, the most important factor and the key factor is to have reliable and reproducible data. So we keep talking about measurable PFAS, occurrence, fate, but we need to have a reference and the method that can give us the reliable and yet reproducible data. So there have been different agencies trying to release different analytical methods, and we have been seeing different EPA methods, starting from EPA method 537 that was released in 2009 that started with only one matrix that was drinking water. And it was only targeting 14 analytes. And as we all know, working with PFAS, we have about 9,000 different PFAS. So it's very important to really expand the list of targeted compounds when it's come to PFAS. And this list has been just getting expanded, and the matrix has been getting expanded until now that we have the EPA draft method 1633. As like an individual working on PFAS, I think everyone was very excited to see a reference method finally out there that we can apply to a variety of matrices and our different projects. It covers groundwater, surface water, wastewater treatment, plant samples, soil, and tissue. And the targeted method includes 40 different PFAS compounds. It has different polyfluoroalkyl acids, some of the FDSs, some of the FDCAs, and this is a very comprehensive and easy to apply method, but still have its own challenges. And as I'm gonna continue talking about analytical methods, I want us to keep in mind that we're talking about all the targeted methods, and we will not be covering suspect or non-target. So as I mentioned, 1633 has been a good reference method so far, but of course it has its own analytical challenges. First of all, I would like to focus on the management. So basically, when there is a complicated method like 1633 that carries a lot of steps in it, then it takes time. And when it takes time, the commercial labs or the academic labs, the turnaround times go longer. And then the other problem is that once this is the most favorable method, then most of the agencies or clients are asking for 1633. But then it actually makes a lot of samples being submitted to commercial labs, and that's why we are experiencing longer turnaround times than promised turnaround times, and of course, a lot of backlogs. Like for one of our largest projects, I know that we have submitted over 1,500 different samples to a couple of commercial labs. And then the other side is the technical aspects of this. So it is correct that we can apply EPA 1633 to all of the matrices, but we need to be careful. What we are seeing in this slide is a peak that has been recognized as a perfluorobutanoic acid, or C4, in one of our environmental samples. And this peak has been getting integrated as PFBA, where we were experiencing a large variability. That made me to go back and look at the data closer. And once we do that and compare this to QA/QC samples that you see the matrix spike, you realize that the peak that is actually spiked is not the PFBA. So it is clear that there is an interfering peak that is being integrated as PFBA. And this was further confirmed when we injected the very same sample with a different chromatography method that had a better separation, which showed us that the peak was clearly separated from PFBA. And we later injected the very same sample in a high-res mass spec. And what we saw was another peak, so it was not PFBA, but it was getting integrated as PFBA for most of the samples. So this is another problem that comes when you are applying this method to, or similar methods to, very complex matrices. So what it means is we should have a very comprehensive and true review of the QA/QC samples that are meant to be serving the same purpose. And there was a recent publication by Bangma et al. That found the interfering peak with PFBA to be as saturated fatty acids in some of the environmental and tissue samples. Then the other analytical challenge that comes with evolving all the analytical methods is when it comes to field assessment, screening levels, or whenever we need some quick data to make some decision or to make some further steps. So we are used to use EPA method 8327, which is a direct inject method. So the direct inject method, of course, will have lower costs, shorter turnaround times, but then the drawback is it will have high limits of quantification, as high as 20 ppt for PFOA, that now we know that with low MCLs that were just released by EPA, this is very high limit of quantification for some PFAS. And then on the other hand, we have EPA method 1633, which of course has higher costs, longer turnaround times, but low limits of quantification as low as 0.6 ppt even for complex matrices. Then so far what we looked at was mostly the targeted PFAS and the analytical methods that have been covering the targeted compounds. But when it comes to PFAS, as I mentioned, we have over 9,000 different PFAS. And if we are limited to targeted PFAS, then we will be only seeing a small portion of the iceberg. So one of the convenient and yet accurate methods of looking at the fluorine-based PFAS or total PFAS is total oxidizable precursor assay. This assay was first introduced by Houtz and Sedlak in 2012. And since then has been applied to different variety of samples. And this method is based on indirect measurement of oxidizable precursor. So basically you have a total oxidizable fluorine content in your sample. Then you make the conditions alkaline, then you add persulfate where you are creating some of the reactive intermediates like hydroxyl radicals to make them react and oxidize the precursor to generate some of the PFAS that we can actually measure as targeted PFAS through our conventional methods. So basically by comparing your total fluorine before and after oxidation, and then the difference will show you the oxidizable precursors or oxidizable fluorine content. This method was first introduced for aqueous samples, but have been applied for both aqueous samples and solid samples. So for aqueous samples, it's usually you just oxidize the samples directly. And then the limitations that it has is the high organic content, because it's obvious that once you have the reactive intermediates like hydroxyl radicals, they are not selective towards PFAS only, right? So they will just get oxidized any organics present. And it might be outcompeting the PFAS. So this for solid samples, so what have been offered by analytical labs so far is to extract the samples and oxidize it. And so it will be almost the extractable oxidizable precursors. But there have been some efforts to directly oxidize solid samples by digesting the organic contents, but this method is not currently being offered by any of the commercial labs that we are aware of. And I should mention that there is no reference method for total oxidizable precursor assay out there, and people are just modifying based on the initial method that was introduced by Houtz and Sedlak. Then the other method that we can apply for PFAS is total fluorine methods. So there are different methods to look at the total fluorine, and the most common one is combustion ion chromatography or CIC, which is basically combusting the sample and converting all the fluorine content to hydrofluoric acid and then making it to scrub to fluoride and then measure fluoride as inorganic fluoride in ion chromatography. We have graphite furnace atomic base approaches and also particle-induced gamma ray emissions. But I should say that the graphite furnace and PGLs are not that mature yet and not being offered in larger scales for larger amount of samples by analytical labs. And for combustion ion chromatography, I should add that it can be applied for both aqueous samples and solid samples, but it should be a slight difference between these two. And we have method 1621 released by EPA that is covering the aqueous samples. So for total organofluorine, when we are applying it to aqueous samples, it is basically called adsorbable organofluorine. And the reason is that for aqueous samples, the sample is being passed through a adsorbent and mostly activated carbon. And then the media is combusted. And then this is why we call it adsorbable organofluorine. But when it comes to extractable organofluorine and it's being applied for solids, basically you extract the solid and you could follow any extraction method appropriate, including 1633. Then the fluorine will be in the extraction and then you combust the extraction. And then, of course, there are limitations for both of these. And the main limitations that comes with AOF, or adsorbable organofluorine, is high tendency of activated carbon for any organofluorine. And it's not only PFAS. So basically, you will end up having organic fluorine coming from pesticides, proteins, or pharmaceuticals. And that's why that interfering fluorine is problematic. And we have different ways to actually get rid of the inorganic fluoride, because sometimes you have background fluoride, and usually you just extract the gag with a solvent to get rid of fluorine, or like with a aqueous solution like sodium hydroxide to get rid of the fluoride, and then you do the differences. And that's true for extractable organofluorine too, because none of the extraction methods are completely selective towards the PFAS-based fluorine. So with this, I would like to focus on the importance of analytical methods, even when it comes to forensics and fingerprinting. And as I mentioned before, if we want to do a management on contaminants like PFAS, or like track down the sources, we should have reliable methods. And any of the analytical methods have their own benefits, starting from our limited targeted analysis to total organofluorine, suspect non-target analysis, and some of the diagnostic ratios that can be achieved by having reliable analytical methods that will help us to have a better sense of fingerprinting or forensics. And once we have the reliable and reproducible data, then we could apply the statistical analysis like principal component analysis or different machine learning classification algorithms to see if we are seeing any clusterization or categorization of different sources. So I think with that, I would pass to Mike.
Okay, thanks, Masa. I appreciate that. So I'm going to pick up now. I think Paul introduced early on in his slides, the rebirth of the remedial investigation. So for the last 20, 30 years, we've been working as an industry on getting through the remedial investigations, site investigations, getting a remedial action, and implementing remedial actions. And this date of 2020 is really my date, where we started putting in remedies and started finding that sometimes the remedies weren't working exactly how we wanted them to. So, either the plume wasn't shrinking the way we wanted to, or the source area wasn't degrading as fast as we thought it would. And that really kind of got us looking, more in depth at these different areas, in the high resolution site characterization, environmental sequence stratigraphy, HRSC or ESS, have become tools that we've used to kind of look at these remediation problems. And what we really figured out was, 80% of the mass transports through 20% of the aquifer, right? So we really got to find, two different areas of the aquifer, and I'll get in a little more description in a later slide about that. But so this means that we have complex problems we're solving for TCE and benzene and those contaminants. But guess what else is complex? PFAS is complex. PFAS plumes are huge because a number of factors, right? The thresholds, the regulatory thresholds or the human health thresholds are really, really low. They don't degrade like other contaminants, right? There may be some biotransformation or precursors along the way, but for the most part, they don't degrade. So you end up with these very, very large plumes that are very, very long. So now we're implementing these long, these tools into our RIs now, right? So we're getting back to the RIs, and we've learned so many lessons through the history that we're applying to PFAS now. The image on the right, comes from ITRC. It's a 2022 document. I think it's really applicable. What does this mean? If we're doing, high resolution site characterization and ESS early in the process, that's going to cost more. And what this figure shows, the blue line shows, cost against time. And yes, it does cost a little bit more than without, these other advanced characterization tools. They use RDC or remediation design criteria. But, what it's going to show is that you're going to shorten the remediation timeframes overall and for less cost. So what is HRSC? It's a term that's used for just really high density sampling. And when do you need it? You kind of have to evaluate your site, your contaminant, your pathways, your receptors. Really, if you have a large sandbox for an aquifer, maybe it's not as applicable. However, if you're looking for an ancient river deposit or an ancient riverbed that's meandering, that's 100 feet wide based on your analysis of the site, and you really need to find the location of where that transmissive portion of the aquifer might be and where the low hydraulic conductivity material or the low K units are, that might be a source of back diffusion of contaminants over time, you might have to like reduce the scale. So, you want to look at your site and is it birds or is it algae that you need to look at? Really, it's about developing that conceptual site model and refining that conceptual site model. We've learned the power of that tool, right? Really kind of feeding that understanding of the site in 3 dimensions. And what better way than to give 3 dimensions to your site than providing that data? So HRSC data usually comes with the 3 dimensions, X, Y, and Z, but then it also gives a value. So now you're able to readily plot that information using visualization programs like EVS or Leapfrog or other programs that are out there. And what you get is a representation of the data, the subsurface, the contaminant plume that could be viewed not only by you to process as the project team, but then also by the stakeholders who can readily accept understanding of the CSM and move to the next step of the project. So what's the big deal about HRSC? What are we really looking for? The image on the right is a pretty famous tank experiment done in Colorado State. And what this is a tank, an aquarium tank that has sand and clay, and it was saturated with a dye, right? So it was held with a dye, and then the dye was released and flushed through from left to right. And once you really understood, this was meant for kind of those legacy contaminants like TC, but those clay units, they tend to hold on the contaminants and then allow them to diffuse over time. As the more transmissive portions, the sand portions, kind of clean out. This is applicable to PFAS because PFAS does like to absorb to fine-grained particles in the aquifer. So we really need to know where those areas are located. So that's where HRSC kind of comes into play. When we get to actual remediation, and Paul's going to talk about that later, the different tools we have, and a lot of them are still being vetted. But our whole concept, we did this with our legacy contaminants, is to come from the image on the left, the bottom left, of a groundwater pump and treat system. This is working right now for PFAS, but we want to get it to where it's more targeted and surgical, right? We want to focus, maybe different technologies or different remedy types for the source area. That may be more where the low K material is, the transmissive portion, where it's transporting. So we get it where it's moving down gradient. And the total plume, that might be a compliance issue. You might have a drinking water well where you have to have some remedy in place that's going to prevent it from migrating. I'm not going to go too far into this slide right here, but these are examples of HRSC tools that are available. They basically break down into 2 types, right? They're about understanding hydraulic conductivity, at depth, and then also getting the vertical stratification of the impacts with depth. They are also applicable to overburden and for bedrock. So I wanted to kind of give you a case study that kind of incorporated some of these HRSC tools. This is an upper Midwest site. It's a glacial environment, so it's very complex. There's regional groundwater pumping in different areas that could affect groundwater flow. EA was contracted to do a phase 1 RI, and the pink rectangles on the right figure represent, the identified PFAS release sites, right? So these are the likely locations. And based on the information that was available, there wasn't a whole lot of investigation at this location. And in the information, the wells were very infrequent. They were closely spaced. And the regional information said that the groundwater flow should go to the southeast, which is to the right where that big blue box is with a question mark. So that's where the inferred groundwater flow would go that might have PFAS contamination. So this is kind of where we started. But there seemed to be, some problems as we got into the literature search. So we decided that we needed to perform an ESS analysis, really get into it. I think others have described ESS as really good geology, right? So kind of understanding, the depositional environment to get an understanding of, which way groundwater flow should go and what are the size of those, transmissive portions of the aquifer. So our geologists got into this. They took a look at it, found a bedrock, a thickness of glacial drift map, and that's on the left. And what you can see is the site is kind of in the middle with the green, and the red arrow is kind of pointing to the southwest because that's where the dip of the glacial outwash should be, right? So the picture in the middle is kind of representative. It's an analog of what those glacial outwash deposits should look like. That's the transmissive portion of what would be eventually an aquifer. So we have indications that the flow should be going southwest, but the hydraulic information we had said southeast. So that was questioned. So we had to incorporate that into our investigation plan. One more complicating factor is that red dot that says 15 in the figure to the left. That was a pumping well, so that was on at one time. So could that influence flow? So we came at this with, and a lot of folks are doing this with an adaptive sampling plan. So multiple mobilizations. RIs historically have taken a number of years. For TC, maybe 20 years. I think as an industry, we want to get it done faster for lots of reasons, right? We want to understand the site quicker so we can kind of get to remedy when those remedies are available. So this is adaptive. We're getting information, we're processing information, we're looking at it in 3 dimensions with our stakeholders, and then we're making decisions where to go next, or getting agreement on the locations we want to sample. So this is just a toolbox of different sampling that we did. Surface soil sampling to find the source of PFAS. Most PFAS is going to be in the first 2 feet of soil. I think we've seen that across many different studies, and then it drops dramatically after that. Subsurface soil borings to finally get that vertical delineation. Really, the key to this additional investigation was really the aquifer sampling. So using HPT or hydraulic profiling tool with electric conductivity, that really gets you the understanding of hydraulic conductivity at a very refined scale. And then aquifer profiling, which is multiple samples, or vertical aquifer profiling, gets you multiple samples with depth. So the image on the right, the red squiggly line is your hydraulic conductivity. The higher the conductivity is further to the right. And the blue rectangles represent our selected groundwater sampling depths. And these are oriented in a transect that is, ideally perpendicular to groundwater flow. So some of the objectives of our study, we wanted to get dense grid approach for soil sampling for the actual releases, right? So we wanted to cast a wide net. The reason is interviews are only so good. People's recollection of where testing was or where the spill may have been are only so good. So you want to cast a wider net. But fortunately, with the releases being shallow and sticking to the first, couple inches to a couple feet, you could do a lot of sampling pretty quickly. One of the other objectives is we wanted to be flexible in our groundwater sampling approach. We were coming out with, direct push sampling. We had to know which way we wanted to move the profiles as we went from upgrade to down gradient. Was it to the southwest or to the southeast? We wanted to use HPTEC to identify those preferential flow pathways as we continue to move down gradient. This is a powerful tool that's available to us, right? The image on the right, the bottom right, is one of the final products of our sampling, and these are transects that are oriented perpendicular to groundwater flow. And this is mass flux or mass discharge of PFAS, right? This is PFOA. And what it really kind of tells you, if you look at the colors, it kind of shows you, the red kind of shows you where the PFAS is, and it's transporting along the most transmissive portion. Mass flux is really just the multiplication of concentration times groundwater velocity. So it really kind of shows you where the transmissive portions are flowing the PFAS down gradient. Other powerful tools associated with mass flux assessments, you can get an idea if the plume is contracting or it's expanding based on some of the data you get out of that. And then you can also start to assess the natural absorptive capacity of the aquifer using this mass flux information. And that's going to be beneficial not only for the site itself, but down gradient. You can extrapolate what's occurring down gradient, how the depositional environment is, and the amount of low K material there is down gradient. You may be able to figure out, is that enough to kind of halt the PFAS plume? And this may be important as we get further along into, remedy development, because with such low concentrations and high costs associated with treatment, we're going to need some sort of natural attenuation portion to our remedy. And then, of course, we wanted to have frequent data presentations of the project team so we could get their buy-in as we move this project forward. Next slide, please. So some of the results I just wanted to give you kind of where we got to with this. Groundwater flow direction, for us to figure out which way was actually happening in the field, because we didn't have wells to gauge, we used a combination of the USGS digital elevation models and our HPTEC results, where we found the water table. And we were able to quickly determine that groundwater flow direction using that assessment was actually flowing to the southwest. So with the first couple of transects that were perpendicular flow, we were able to continue down to the southwest and ended up generating, what looks to be a, contiguous groundwater plume to the southwest. Finding out probably that red well that I talked about earlier that's on the right side of the figures here was pumping during, the investigations and may have had some influence, but generally groundwater flows to the southwest. This happens on a lot of projects, but especially when you have this kind of high density sampling, is that you start finding new things, right? You start finding other sources that look to be shallow groundwater impacts in areas that you didn't expect. So, okay, what's going on here? Then you can talk to your stakeholders, you present the information, show the data. That red oval on the left figure, there was a couple of high concentration areas that looked like new sources. Going back to, the project team and to the stakeholders, and found out, yes, there was a couple of unreported at the time, testing areas, and those could have been the likely additional release areas. And then what's going to be shown on the next figure is that, we expected vertical migration to be significant, and it sure was at, greater than 100 feet. So, to kind of come to conclusion, the cross section that's shown on this figure right here is actually oriented from up gradients on the right this time to down gradient on the left. What we have here, I'm sorry, it's up gradient on the left and down gradient on the right. What we have here is it is matching our conceptual site model that we got from our ESS analysis that, you're seeing these transmissive portions of the glacial outwash going down and deeper from left to right, and you have lower K material or lower hydraulic conductivity material near the source area. That kind of fit the model. It all made sense. Some of the advantages that we got out of this, we were able to quickly modify our characterization axis based on what we were getting in the field. So, this real-time data acquisition and processing helped us to continue to move in the right direction, identify these new source areas, and quickly with our project development team, identified that, yes, they are probably new source areas and something needs to be done about those. But the big thing that we got out of this project, is that I kind of looked at this. This ended up being about 1.5 miles long plume. Historically for other, contaminants, we looked at something like maybe 100 wells for about 1.5 miles long plume, right, to these depths. When we worked with our team and we had this characterization data and, this high resolution data and really got the plume kind of mapped out, we determined that really, monitoring wells are for monitoring. It's kind of long-term monitoring. We don't need them for characterization. So deep wells to over 100 feet cost a significant amount. So, putting in 26 wells really optimized the cost for the RI and really kind of paid for the HRSC investment that, generated a lot of the data that we collected. And then kind of building off of what Moss has started with, talking about some of the different analytical methods that are out there right now. She had a slide on the difference between 8327, which is, useful for field screening versus what is 1633. There is a need, I think, for this kind of high density data, especially for these PFAS sites. And the problem is when we start getting, draft method 1633, which is a great method, but it still has some bugs to work out, rather difficult to implement right now. And then there are some logistical problems as the industry kind of, ramps it up. But it's rather expensive, when it comes to these HRSC purposes. There are hundreds of dollars per sample. So we're looking, I think as an industry, we want to get something a little bit faster and a little more cost effective that gets the data quality that we need, especially near these source areas as we try to figure out, which way it's going and where the highest concentrations are going. What's really cool right now is that there's a lot out there right now in the R&D world looking at these electrochemical and biological detectors. They're probably a couple of years away from, going full rollout, and there's a lot to be done. There's lots of selectivity and sensitivity issues with them right now, but there's a number of them out there. And this article headline right here is just from April, as the race is on for these low-cost PFAS detectors, not only for remedial investigations, but maybe for wastewater treatment plants and water treatment plants for their compliance sampling. So while this is all being developed, there's still a need for those, in my opinion, those other analyses so we can get this high density data to get rapid delineation for PFAS. That's it for me. I'm going to turn it over to Cynthia to talk about toxicity.
Thank you, Mike. So after you've performed your field investigation, your analytical data that you get, you usually subject that to either a risk-based screening numbers or perform a risk assessment to determine some effects. And a very important part of both of these exercises are toxicity values. However, we only have toxicity values for a handful of PFAS compounds. Why? Well, a number of things. First of all, the number of PFAS. As Paul had mentioned, over 9,000 PFAS compounds, and we have not determined a unified way to evaluate mixtures. PFAS are not metabolized by the body. They travel through the body within the blood. This results in PFAS producing a wide range of health effects throughout the body. As the figure shows, they can affect various organs such as the kidney and liver, or systems such as the immune system and cardiovascular system. PFAS can also cross the placental barrier. Not only that, the effects can differ based significantly upon individuals that are exposed. PFAS have a longer half-life in males than females. The half-lives in animals can be relatively short, measured in hours to days, compared to humans, which is generally measured in years. So they're not readily eliminated from humans. Not only that, recent studies, especially of PFOA, have revealed uptake and reuptake in the gut. The kidneys also can reabsorb PFAS, reducing the elimination from the human body. And because PFAS usually occur as a mixture, the contributions from different PFAS have to be taken into account, especially when we're evaluating the human epidemiology data. Also, PFAS are present in consumer goods and environmental media. As Paul said, we're finding it in rainwater. There's transfer during fetal development and in breast milk. So due to PFAS widespread use, their presence, persistence, and bioaccumulation potential, many PFAS and toxicity studies are detected in the toxicity studies. However, when the exposure or the effect occurred can be difficult to determine. So exposures and PFAS levels causing effects can be difficult to measure or correlate. So what information do we have? The following is just an overview of the toxicity values that the US EPA sets forth or presents on their regional screening level table. The RSL table, I think this is a table that most of us use, especially for comparing our results just to see what we have. We really only have 4 values right now that have been finalized or set forth by EPA. The toxicity values for PFBA and PFHXA are finalized by EPA and their IRIS database, so those are not likely to change in the near future. EPA released a draft oral RFD for PFDA on April 10th with an oral reference dose of 4 × 10⁻⁻10, which right now is the lowest oral reference dose for any of the PFAS. It is noted, though, and EPA made this a note, that PFDA is a recent PFAS that is now being detected in human blood samples. The PFHXS and PFNA are in the preliminary stage. Their toxicity assessment was also presented in the MCL determination. And these are also two additional PFAS that are starting to be detected more recently in human blood samples. And the PFBS is a provisional peer-reviewed toxicity value that EPA has set forth. So these values are probably not going to change in the near future. The other toxicity values presented on the RSL table are taken primarily from the 2021 ATSDR document, and those are still being used to this date. However, I'll note that there are implications to toxicity values when EPA has released their draft MCLs. They present new toxicity values for PFOA, PFOS, and PFHXS. And these values are more conservative than we are currently using based upon the ATSDR 2021 document. The values are 10 to 100 times more conservative. So another change is the MCLs for PFOA and PFOS are based upon a level that can be reliably measured because both compounds are identified as likely carcinogenic to humans. EPA noted that PFOA is identified as a more potent carcinogen, so it will have a more conservative cancer slope factor, and PFOS is now identified as a carcinogen. Both changes from currently the way we are assessing them. And I'll note the hazard index approach that EPA is proposing for the PFAS is slightly different than the hazard index approach that we currently use in the EPA Circular Risk Assessment Guidance for Superfund. So this may be a potential way that we're going to deal with mixtures in the future. So the proposed changes for both PFOA and PFOS alone would likely affect previous risk-based screening levels or risk assessments performed for sites with these compounds. And it's a concern, especially if no risk concerns were identified. And additionally, I also want to point out there's a lot of discussion around the draft MCLs, especially for PFOA and PFOS, and whether they will increase or EPA will leave them at the 4 ppt. I'll just note that if the toxicity values presented in the MCL toxicity assessment, the backup, are finalized by EPA, these are the values that will be used in any risk assessments or screening levels. So you may have an instance where your site does not exceed the MCL. However, the risk assessment may reveal a potential concern for human health. This is a situation that we have dealt with for some other chemicals like arsenic. So that right now the toxicity values for quite a few PFAS are still in some flux. We're getting a lot of data very fast, but some uncertainties are going to remain for a while. So here are some observations or lessons learned that EA is finding as we progress through both investigations and risk assessments. So PFAS risk assessments may require evaluation of sites or sources that are not typically evaluated or that we did not previously evaluated. EPA is performing a risk assessment for land application of biosolids, and this assessment will provide valuable information for risk assessments and assessments of other non-traditional exposure pathways, like we've mentioned below, like agricultural crops and livestock. Wastewater discharges, we normally do not evaluate those in a risk-based manner, but currently we do not have any water quality criteria or even draft criteria for PFAS for the human health endpoint. So these discharges are an additional source that we may evaluate. Spills and training areas. We would previously evaluate fire training areas, especially for chlorinated solvents. However, other areas like Mike had mentioned that normally we don't think about are also coming into play. And also we are or may evaluate or change the way we evaluate some exposure pathways. And I'm going to kind of focus on the fish ingestion pathway. We would typically model a fish tissue concentration based upon a chemical concentration in surface water or sediment instead of collecting fish tissue samples. However, the modeling approach for PFAS is becoming problematic due to the uptake factors of PFAS that can be greater than 1,000 times the surface water concentration. Also, the uptake is dependent upon the PFAS mixture. The uptake factors for individual PFAS can decrease when a mixture is present, so site-specific uptake factors are more appropriate than default values. We're also finding uptake in lower trophic fish can be as high or higher than those of higher level predators, which also kind of speaks to which fish species should be collected during sampling. So from the risk assessor point of view, we see more benefit to collecting the fish tissue samples initially if a water body is present near a site that has either soil or groundwater PFAS contamination or other PFAS discharges to a waterway, instead of waiting until the assessment is completed. So I'm just going to summarize. When evaluating PFAS, it is very beneficial to include the risk assessors coming from a risk assessor early in the process to assist with identifying both your sampling needs, that you'll need to complete a full analysis and also kind of discuss kind of what's going on with the toxicity values, because that's going to speak to your screening levels and potentially what detection limits you're going to need in your analytical methods. Additionally, I'm going to caution that any sites or areas that were previously determined to not be a concern should be reevaluated with the newer toxicity values or proposed values to assess any impacts. And finally, just keep in mind, we do not have toxicity data for the inhalation or the dermal exposure pathways. So these uncertainties will also have to be taken into account in the future when you're evaluating your sites. So with that, I'll turn it over to Paul to discuss some remediation.
Thanks, Cynthia.
Options.
Hopefully you can still hear me here. I'm going to go through these real quick so we can have a little time for Q&A. So this is a bit of an eye chart, but the takeaway from this is granulated activated carbon and ion exchange resins really are the tried and true treatment for public drinking water systems. When we look at municipal wastewater treatment systems, I don't think that these GAC and ion exchange resin will work on these larger systems because of the quality of the influent at these wastewater facilities, as well as the large amount of residuals management. But there is some technologies out there. One of my favorites is foam fractionation, which takes advantage of PFAS, certain PFAS affinity for the air-water interface. That would be bubbles that we create a foam, and then we skim that foam off the surface with high concentration PFAS that can be treated later. There are other technologies on here, but by and large, they're mostly applicable to lower volume, higher concentration waste streams. Likewise for soil, really what we have now is landfilling, but there's regulatory flux. How will this stuff be handled under RCRA or maybe CERCLA? Thermal is one of the technologies that can actually achieve complete and irreversible destruction of PFAS. But there's some data gaps that have to be filled by the scientific community on how these what emissions come out of the treatment system. And again, there are other technologies that are under development, but I think most of them are more dealing with the higher concentration, low volume types. But there's always a preference for destruction over moving reliability from one place to the other. So, as we look at the technology readiness level paradigm, there's a lot of technologies out there that are under development. But really, I think once we deal with the drinking water situation, the next big challenge is going to how to deal with PFAS in the 34 billion gallons of wastewater discharge daily from more than 16,000 municipal wastewater treatment plants nationwide. That amounts to about 10,000 pounds of PFAS discharge annually into our nation's water bodies. So finally, I want to close with a couple things. Right now there's estimates that PFAS could cost us over $200 billion over the next 20 years. As we develop, lower detection limits, we're going to find more PFAS. The question is, can we really clean up all the PFAS that we find? We haven't been able to do this for the chlorinated solvents to this point. And what happens if more PFAS are regulated in the future? So from my perspective, the PFAS science has evolved in the following ways. We need to really look at the CERCLA framework, how we investigate and remediate these sites that we've been working under for 40 years. Maybe we need to look at it a different way and first clean up the drinking water that people drink, then make an effort to limit further releases of PFAS into the environment, and then maybe tackle the remaining sites based on their highest potential for risk. So with that, I'm going to turn it over to Amy to close out.
Now let's turn to Q&A. See, open up my window and see if I don't see any questions yet, so maybe I can prompt something. Paul, with PFAS now such a significant focus within the environmental remediation industry, what percentage of overall funding is currently being dedicated to PFAS research and cleanup, and how do you see that changing over the next decade versus other remediation types?
Well, I think the U.S. environmental, depending on how you define it, is about $7 billion a year. That includes, remediation and investigation, $7 billion. And looking at those projections, that was a Environmental Business Journal projection that was input by other companies like EA. American Water Works Association also had their own estimate for their drinking water providers. But I think we're already seeing a lot of money going. DOD has taken a lot of their munitions response money in the past and moved it over. It's revitalized the remedial investigation. And I think EPA is getting on board. We're starting to see sites now where they're starting to take a look at it. So keep in mind, this is all without any kind of unified federal regulations. So I think the shift is going to move more money to PFAS for the foreseeable future.
Thanks, Paul. Anybody else have any questions? I see a hand up. Greta, can you type? Let me see if I can release your microphone. Hold on for a second. You should be able to unmute now and ask your question.
Yes, thank you. The chat is turned off, just so you are aware, and there is no Q&A that I see, so I don't know if that's why people aren't asking questions.
Okay.
But I just wanted to know if you could speak some more on the fractionation as a remediation technique.
Well, I'll start, and maybe Masa or others can jump in. But right now, it's been looked at mainly for landfill leachate and some groundwater treatment. Ex situ. A lot of it's surfactant enhanced, so they can get better adherence, I guess, of some of the PFAS to the bubbles and get higher enrichment rates. But we're looking at possibly looking at this for wastewater treatment. I think if you look at a lot of the wastewater treatment plant facilities, the way they do their treatment, they already have aeration tanks, and they have large open tanks, and some of them have dissolved air flotation, and a lot of them create foam incidentally anyway. So I think one area is the wastewater treatment. There's companies out there now that are looking at in situ remediation, basically creating bubbles and pulling out foam in situ with some of the with a well, so that you don't have to have any extracted groundwater. But most of the work right now has been there's more work to be done, but most of it's been focused on landfill leachates and pilot systems.
Oh, wait, a question just came in. For PFAS, is it justified to single out landfills and wastewater treatment plants as responsible parties for managing them?
Oh, I think, well, first of all, I'm not sure that, I think they're innocent bystanders. I mean, they receive waste. They're not set up to treat that type of waste. PFAS is an emerging contaminant. So I'm not insinuating in any way that they're PRP. So I guess the short answer is no. I don't think they're justified. I think there should be some kind of way that they've made whole. I mean, this is not their problem. So I hope that came across, and I wasn't indicating that I thought that they were the culprits.
Okay, question, are you able to complete an RI without ecological risk factors?
I'll let Cynthia take that one.
So since I'm human health, I can only say that no, they are it's same way rapidly developing, the same way the human health numbers are. They have some of them that are out, however, they're pretty high. And so right now, human health is the one that's kind of dominating any risk assessments or things of the nature in the RI.
Great. Next question, is or will PFAS require any special certification or remediation for remediation or investigation in the future?
I don't think so. I mean, right now they're not a CERCLA hazardous substance, and they're not covered under RCRA. And they're just, in fact, there's less guidance on what to do with this. But in the future, I think if they promulgate MCLs and there's other criteria, we'll deal with it like we do any other, organic waste.
Got another one. Which method will be the best choice for screening purposes?
Well, I guess I'll jump in on that one. So, it's really up to, that's the easy answer, right? It's up to the project development team. But for groundwater, the direct injection method, 8327, is kind of a leading one. And then for soil, it's the ASTM method. You look at that one for kind of rapid screening.
All righty, well, with no other questions, that concludes our webinar for today. Thank you so much for joining us.